Hi everybody, my name is Kevin Kempter. Today I'll be talking about data architecture with Postgres. I work for a company named Consistent State. We're a Postgres consulting shop. And we offer a number of services. A couple of them in particular have led us to the place where we are more and more being intentional, if you will, about doing data architecture as opposed to just Postgres consulting. So we do, obviously, traditional consulting. Our newest service is the data architecture as a service. We have a rapid review, which used to be a database health check, and today it's more of a data architecture assessment, which includes a database health check, and we do training. I throw these out to make the point that as we've engaged in consulting throughout the years, we find more and more that once we hit the ground for a client, that in addition to database admin and performance tuning and help us with backup and recovery, we start to creep into the data architecture or data layer areas. And I thought it might be beneficial to present some of what we've been seeing and in terms of talking about data architecture and then talking about how Postgres specifically fits a sort of run-of-the-mill data architecture. So in terms of just definitions, to make sure we're all on the same page, data architecture includes a data strategy and business process improvements. The business process improvements are generally, from our perspective, a combination of monitoring and looking at metrics and assessing risk, and then letting those risk assessments drive a priority list for a continual improvement process. And then that continual improvement process will start to drive the architectural direction of the enterprise, if you will. And not only the database layer, but data management layer and everything to do with data architecture. Those two components, the data strategy and this continuous improvement process, will drive and support decisions of the future of the enterprise class systems, if you will. It'll drive integration efforts and standards. It'll drive our data warehousing or BI or general reporting approaches. And it'll drive the executive level folks' ability to justify spending X or spending Y on certain changes. So those two components then in turn support all of the things that we would consider data architecture. And really what it often comes down to is twofold. A, what's my scaling strategy? And B, can we grow the business and still deliver our business services at the same level of service, if you will, to our customers? And that's generally the bottom line for anybody at the management level and above, the database manager or the executive level folks. That's their bottom line, at least when we're talking data architecture or, Postgres plus all the areas that Postgres touches. One of those components is data governance, and to be honest, data governance is probably the most difficult component to get a company or a client to actually follow through with and get something in place. I think A, because it spans all the silos in the company, therefore there's political battles every direction you look. And B, a lot of folks just don't understand either A, what governance is, or B, why bother? I don't understand the need for it. However, the execution and enforcement of authority over basically the management of our data as an asset is really important, and it ties into the database standards that we might define in terms of what our standards are as a company, what roles are allowed to do what, not just at the database level, but with our data as a company as a whole. Modeling standards tend to fall under the data governance area, as well as data integration rules, which will start to define what our data quality picture looks like. Also, the fact that we would have a global or an enterprise data dictionary. I mentioned the data quality standards. Our management of QA and integration and development data sets. What does that need to look like, and are there security concerns? Do we need to mass data? And what's the standards for us, as well as just general documentation top to bottom of everything that has to do with our data layer. Again, this is a tough one. There's a couple of clients that we've convinced to move down that road, but a lot of times we just don't have the support at the management level, or there's just too many people vying for that same set of authorities, if you will, and it never really goes anywhere. So we tend to push on all these components as much as we can, and then as a database shop, in particular a Postgres shop, we will deploy certain techniques and certain approaches that really supplement or enhance our ability to manage data architecture within an organization. One of those areas is data modeling. So it's fine to have an OLTP database model, and maybe we've added some columns for our historical tables, and maybe we have a schema to do reporting. But usually when we first engage, there's not a lot of forethought to what does the model look like today versus what should the model look like 6 months from now, and what do we expect the model to look like 2 years from now. So one of our data modeling efforts is going through and looking at business processes and trying to come back not only with changes that we might deploy for the purposes of scaling in the near future and performance in the near future, but standards that we think are going to support the organization as the organization itself starts to scale exponentially. So to that end, we start to define OLTP standards. So what are our standards? What are the approaches we will take when it comes to our OLTP systems? Hand in hand with that, we'll be managing historical data. There's half a dozen decent ways of handling historical data in the model in an OLTP scenario, and we need to probably pick one and maybe a fallback if there's certain use cases where that one doesn't apply. Reporting and DSS modeling, aggregate modeling, and how we're going to feed those aggregate structures. All of those components will eventually be modeled in reference architectures. So we will have documented reference architectures that will have, in our case, a number of Postgres-specific components that allow future employees and future data guys, as well as the existing employees, to take a look at these reference architectures and understand these are the standards for this organization. So from a data architecture perspective, the Postgres components would include things like use of partitioning and foreign data wrappers in certain use case scenarios, and specific indexing strategies, and maybe we're a JSON shop, or maybe not. Maybe JSON is hands-off, and so on and so forth. So we'll dig into the model, and then we'll dig into data security. So from a data security perspective, there's a pretty big chunk that is very specific to Postgres, because as a Postgres DBA, you're dealing with security and access and encryption and so forth. However, there are some components outside of Postgres that you might get involved with, at least in terms of recommendations of how data security will line up the best in a Postgres shop. So within the database, we're obviously talking about the hba.conf file and the listen address settings and the postgresql.conf and connection details or connection styles. Are we using a connection pooler, and does that bring any security concerns or security caveats? Data encryption rules within the database. And then we start to move away from the database and get into what does our general attack surface look like? And based on that attack surface, do we need data encryption? Are we trying to meet HIPAA requirements or SOX? and all of our at-rest data needs to be encrypted, are we deploying SSL tunnels? And maybe we even do SSL authentication by leveraging the SSL client certificates and so on and so forth. So we tackle data security from a big picture data layer perspective, even though there's a number of areas where Postgres is directly relevant. Next, we start to get into data content management, which includes the metadata that the organization might have. Lookup data is a really good example. In some cases, the lookup data is such that it's very, very static. So from release to release of a particular set of software or a particular version of a utility that this company leverages, they might actually choose to put some of this metadata within a template database, and then our standard becomes, if you're going to create a database, whether it's for testing or QA or integration or even for a new version of production, that template database will include not only the data structures, but even the data for our lookup tables. And that's a really good way to start to version control and manage some of this lookup data and some of the metadata that might be necessary as a framework, if you will, for initially for the developers as they instantiate databases in their sandbox. Next, and actually this is probably not really the right slot for this slide. It probably should have been one of the first topics, because often we get in and we'll do the initial assessment and we'll find that backup and recovery is woefully inadequate. Oh, we have a standby, so why do we need to do backups? Or we've been doing backups for months, but we've never tested them. That sort of thing. So we definitely attack the backup and recover area straight away. Again, we tend to get into some areas where we're backing up and having the ability to recover data that's not within the database. But in this area, we really focus most of our concern within the database, because in most organizations, all of the key data is in the database. Even if it's lookup data or metadata, it's still housed in the Postgres database. So we make sure that there's a solid backup strategy, which often will include maybe a hot standby and maybe PG dumps that are done on maybe a somewhat of an infrequent basis, and then point-in-time based recovery on maybe we're backing up the base backup weekly and we're keeping the wall files week to week, and we're tarring up the whole package so we know which components to recover. The point being, come up with a data backup strategy that actually works, and then make sure that that backup strategy is as automated as we can make it. And then we'd like to follow up with not only testing backups, but automating that process, where either on a daily basis or a weekly basis, we're randomly grabbing one of our backups. Maybe it's a PG dump one week, and maybe it's a point-in-time recovery package the next week, but we're making sure that we can actually recover from the backups. The last time we did this, we chose, because of the way that the client does business, not to do PG dumps. We're only doing point-in-time based backups, and we package that up nightly, which is the base backup from the previous night and all the wall files up through midnight, and then the next night that backup gets tested in terms of we fire up a test area on a new server, and we deploy that tar file, and we create the recovery.conf and then bring it online and run a number of queries to validate, and a report goes out on a weekly or a daily basis validating that we can recover every single backup that we've taken. That leads often to disaster management. How do we mitigate disasters? Because there are going to be issues that come up from time to time. Replication and HA are obviously great starting points, but at some point we start to have the DR site discussion, and we've done a number of very Postgres specific methods for DR sites. In fact, recently we did a setup where we're using OpenStack, and our DR site was in one of the eastern regions, and our regular normal day-to-day production site was in the western region. Therefore, we have two networks, obviously, or two separate network stacks. What we did in that case is we used PGPool, and PGPool was able to reach out to the DR site as, quote, a slave, but that was only for load balancing reads. If we ever lost the primary site, then the same PGPool would continue to work because we had one in each side, and we had a heartbeat in between the two PGPool instances, which allowed us to eliminate PGPool as the single point of failure in the system. Therefore, the only real caveat when we failed over to the DR site was now we're in a new network, and we would basically update the IP behind the DNS that the application stack is using, and then as soon as that propagated, which is about 60 seconds in this case, then we were on the new stack. PGPool would then take care of promoting the database from a slave to a master, because it would detect that the primary stack, i.e. the master, is gone, and it takes care of the promotion for us. The only real tricky bit for us then became, how do we automate that update of the DNS, and how do we make sure that all of the people trying to access the application are forced in terms of a reconnect scenario. And that was managed at the network layer, and it worked pretty well. And once we got past the DNS issue, the PGPool scenario worked flawlessly for us. In fact, with the latest version of PGPool, I've done a fair amount of testing and found that I can bring the master down, and PGPool will execute the failover, and then I can bring that master back as a standby, and PGPool will automatically start load balancing if we've configured it as such. And then I can basically do a swap. I can bring the secondary master that PGPool upgraded, I can bring him down and then reset him up as a slave, therefore getting us back to our original config. And the only caveat is that existing connections get thrown into an error state and have to reconnect. And once they reconnect, it's seamless. So PGPool is actually one of the tools we use very often in the disaster management / HA scenarios. Next, we inevitably will get into data analytics and big data and BI or data warehousing, or some sort of reporting. This is from one of our recent clients in terms of what we came up with for what they're going to do moving forward with respect to data warehousing and doing some enterprise-wide reporting. So in this case, we have a number of connections coming into the OLTP database, and out of the OLTP database, we are not only ETLing data to the data warehouse, if you will, but we're also populating an ODS so that we can have reporting that's, say, 30 to 60 days old, but it's near real-time reporting. We're not waiting for the ETL process to run and for the aggregation processes to take place and for that data to get pushed out to the data marts. We just come, and in this case, it's nothing more than another schema in the OLTP system, and then we've replicated that schema with Sloaney out to the ODS. So from a read-only perspective, the ODS is just available, and then we leverage the ODS and the OLTP stage, which is another set of Sloaney replicated tables in these guys' case. And we have a nightly process that will then run and aggregate the summaries and the roll-ups and build the common dimension tables and so forth, and then trigger the ETL process that pushes that data out to the data marts. In this case, data quality was managed in the ETL going into the data warehouse, and business rules are managed going out of the warehouse into the marts. That's not always what we need, but this is just an example of one of the areas where we were able to build somewhat of a classic data warehouse architecture, and we're able to leverage a number of the Postgres specific components to help pull that off. In this case, we leveraged Sloaney in order to pull this off. One of the things that we've done elsewhere with Sloaney and I get to it a little later, but I'll just jump ahead anyway, is we will leverage Sloaney in such a way where we will take a certain set of tables and we'll replicate them out to a schema, let's say in the base layer of the data warehouse, and then we will modify the Sloaney tables to say that they're allowed to fire triggers, and basically every time data gets updated or inserted or deleted from those tables, from the Sloaney tables, not the OLTP system, then it will basically insert a row into a CDC or a change data control table. And that row will have all of the relevant data columns from the replicate table, and it'll have what the operation was, insert, update, or delete, and it'll have a timestamp. So when it's time to come back and do our diff processing to build our aggregates, the diff process is actually already done for us. We just go after those CDC tables, and we can grab all the inserts, and we can order them by timestamp, and we can take care of business in our aggregates, and then grab all the updates, and then come back and grab all our deletes, and it makes that change detection process very easy to manage. I think we could pull this off with PG Logical as well, but to date we've only done it, actually implemented it with Sloaney. Data lifecycle management is a key area too that sometimes gets pushed under the rug, if you will. One of my big beefs here is when we're releasing software from version to version in a database-centric atmosphere or environment, that often will roll out components of that release that will do things at the database level that are very difficult to roll back. So they'll go in and update data in the lookup tables, and they'll modify data in another table, or maybe they'll drop a column from one of the big tables. And then we get into these scenarios where integration testing went okay, but we roll it out into production, and then they find that, oh, we didn't really think that through, and now we can't get back to square one. So we generally approach this one by trying to force the issue that if you're going to release anything that touches the data or the DDL at the database level, that you have to build a rollback script, and that rollback script has to be tested, and it has to put you back to exactly where you started before that release. To be honest, it's a tough sell because that's much easier said than done, and a lot of organizations don't want to spend the extra time. They just figure when things break, we'll just grab the DBA and say, go fix it. And they don't really think about, the opportunities for that to get out of control, which we've seen. And it's probably a 50-50 split, if you will, between the companies that we convince to enforce this strictly versus the companies that say, well, if it works out, that's fine, but don't spend too much time on it. This is a pretty critical area because you can get into scenarios where you just can't get back to square one, and now your data isn't lining up with the release because the application guys have backed off their version to the previous version, and now you have to go in and start massaging data, and that can be a lengthy process with somebody breathing down your neck the whole time. Next is the scaling. So we almost always get to the scaling discussion when we're talking data architecture, and predominantly we're either going to scale up, meaning we're going to scale within a single server, or we're going to scale out, meaning we're going to leverage multiple servers to facilitate our ability to scale the organization. Scaling up means, let's add some memory, and maybe let's add some CPU power and so forth. We can start to do things like data partitioning. In particular, in addition to performance management, we can use data partitioning for historical data management. So we can create a table and we can partition it. Let's say we partition a table by month. We can go into those oldest months. Let's say we're going to keep 18 months worth of data in that table, and as opposed to dropping that data, we can simply uninherit it from the master, and then we can re-inherit that same partition to a historical table so it sticks around for a while longer, but it's not having to be scanned for day-to-day operations. Therefore, once we hit another benchmark, say it's 24 months, and we say we really don't need that data anymore, then we can uninherit it from the historical table, possibly leave it around as a just in case, as a standalone table for a while, and then eventually come back and drop that partition or drop that partition table. Therefore, we're managing history in a very efficient way, and we don't have to do mass deletes which cause vacuum issues for us down the road. We also get into doing things with reporting data, moving data into a reporting schema, which sometimes involves an ETL process that moves data from the OLTP public schema to the same database, but moving it to, say, a reporting schema. And it's really setting the stage for us to move that reporting data onto another server once we get to the point where we can't scale up anymore. I put JSON on there because more and more we're seeing a JSON approach to try to tackle performance, and in some cases it works really well. In other cases, it works really well for a short period of time, and then we're back to making some hard decisions again. But JSON, especially with the JSON constructs that we have in Postgres today, is a very good option when we're dealing with some data that's difficult to eke out the performance that we need. That said, our next step is obviously moving to a scaling out scenario. There's a number of things we can start to look at from a data architecture perspective once we get into a scaling out scenario. One of those is doing some load balancing. So we could potentially put pgpool in front of a streaming replication set of nodes, and we can roll it into load balancing mode, and therefore all of our writes will go to the master and our reads will be load balanced across the two nodes. And that's a really good first step. One of the other things we'll typically look at is setting up a separate reporting server. So we get all of this reporting query activity off of the master and reserve that master's cycles for inserts, updates, and deletes. Therefore, really setting the stage for not only moving those reads off of the primary server, but then giving us the opportunity to refactor that data or relay out that data, if you will, at the model level, so it's really structured for reporting. And we can do that a step at a time. We can basically take that reporting schema and drop it on a secondary server, and then as we go from release to release, start to tweak that data structure and the ETL process that feeds it, so we really do end up with a set of data structures on the reporting server that are geared for performance for read-only query performance as opposed to OLTP style performance. I talk here about trickle feeding or updating the aggregate tables and the CDC tables, and that's largely the Sloaney bit I was talking about earlier. We can also do some connection load balancing, and this usually works best with BDR. In fact, we did some work for a client out in California that had their application set up in such a way that their primary markets were Dallas, Southern California, and the East Coast. And based on that, we set up BDR. They're using the Google Cloud, and anybody incoming to the application on the East Coast would all go to the BDR node that was staged in the Google East region. And then likewise for the Dallas region, we had a Central region node, and then we had a Pacific Western region node, and we ended up segmenting our traffic, if you will, based on where that incoming connection was coming from. We can also do autonomous connection pooling, meaning just do it round robin style. BDR will actually allow us to keep all the databases in sync, and they're all writable nodes, so we can redirect our traffic any way that we see fit and end up by doing some scaling out simply via controlling or trying to level out our connections across all of our nodes. With BDR, of course, it's fairly easy to fire up another node. If we are doing, say, a round robin scenario, we can start to add nodes significantly and maintain a certain level of performance by making sure that our load balance or incoming connection load across all of our BDR nodes is fairly level or fairly relevant to each other across the board. Now, that'll only work to a certain point, but that point is pretty hefty. You can go a long ways down the scaling road simply by managing your incoming connections. If in fact we start to get into the big data scenario and we really need the kind of performance and horsepower that we're going to need from, say, an MPP system because we're doing big data or data warehouse kind of analytics, and just firing up BDR and managing our connections is not going to be enough because it's the back-end ETL processes, then we're going to be looking at something like PostgreSQL, which starts to push into a very specific use case in terms of data architecture. So I thought I'd mention it, but we won't drill into PostgreSQL very much. Another way of scaling out, and most clients at some point, if they're expecting exponential growth of their company, we usually end up talking about how are we going to shard at some point. It might be this is our 5-year plan or maybe even our 10-year plan, but at some point they're going to probably have to shard in order to get the performance they need. We're working with a client right now out of Denver that the BDR thing might work for them, but the downside of that is that they're planning on going nationwide, and if they're successful going nationwide, their traffic is going to grow by just amazing, exponential. It's probably going to be 500-fold of what they're seeing today. So if we have to replicate the entire database across however many nodes we set up, we're going to be trading one problem for another. So they are fully aware that at some point we're probably going to have to shard, which means today we need to be drilling into their model and figuring out when it's time to shard, how are we going to shard? How do we segment their data model in such a way that it's going to be easy for us when they say, okay, it's time to shard, for maybe take a weekend and segment that data and fire up shard number 2 in pretty short order. And if we don't start doing our homework today and start to build some data structures into the next several software releases, then moving to sharding is going to be a big deal because, you know, maybe they come back and say, well, let's do it by customer, and we can do it by customer ID, but their model today doesn't really lend itself to doing it by customer ID because the customer ID is not just one table, and we have to replicate so much data in order to get there. So we've got a fair amount of work ahead of us, but if we do our homework up front, sharding is a really good way to get some significant heft in terms of scaling out. That said, we also have to figure out how's the application going to know which database server to connect to based on the incoming connection. So in some cases we can shard simply by connection pooling. So similar to what I was talking about with BDR, we could say that everybody that connects in this region, we're just going to store their data in this database, and the application stack always connects to the local database server. That works pretty well until you get to the scenario where somebody usually connects in Southern California and now they're in Dallas at a conference and they get in and they want to update their data. If it just shoves them into the local database server, they're going to find that they don't have any data and have to reset up a new account and so forth. Otherwise, you need to validate everybody coming in and say, are they already in one of the databases, at which point we get into this scenario where we're having to hit every database to see if this ID exists, and we kind of shoot ourselves in the foot in terms of initial performance. So that said, we generally look at things like, can we do a hash scenario based on a component of the incoming connection that's always going to be there? Maybe it's a customer ID, or maybe it is a region thing, or maybe it's, you know, some other kind of ID that customer is always going to be related to. And if we can hash that, then we can figure out which database node their data will always live at. Another way to do it is have a single database that everybody connects to, and we always hit that database first and simply look up which database is this customer or this region or whatever we happen to be looking at, which database server do I go to, and then we make the other, so we do two connections. We do the one connection to look up which database server they're at, and then do a second connection. We can also do that scenario, but we replicate only that table, and so that table is replicated across all our nodes. Therefore, if we're doing any sort of connection pooling, the connection is already established, and it simply looks up in the table, where does this ID live? And if necessary, it will reconnect to the right database, and if it's already connected to the right database, then it's all good, and it looks up the customer data. There are a couple of other methods. There used to be a couple of tools, one of them PG Shard, which eventually morphed into the Citus data tool, but the Citus data tool today isn't just for sharding. There is a way to still back into sharding, and they talk about it on their GitHub site, but it's not really just for sharding anymore. That said, there are obviously all kinds of methods of doing this. If you're a JDBC shop, you can have it in a local file that's loaded up into memory as a JSON structure, and so it gets loaded once, and then you do the lookup locally at the application layer or at the web server layer, and then make the right database connection the first time and don't have to do a dual connect kind of scenario. That said, sharding is one of the better ways to scale out in a big way when you need to grow significantly. One of the last components is making absolutely sure that we can track progress and that we can show the organization that we're actually moving you in the right direction from a data architecture perspective. So that generally includes doing some sort of assessment and establishing some sort of baseline. What we like to do is look at all the components we've just talked about, and we rate based on risk factors every one of them. So we'll look at, for example, your data models and your data governance and so on and so forth. And for each one of the components within those areas, we will assign a risk factor based on maturity and scalability and technology fit. Maturity meaning, are we using off-the-shelf components, or based on the data structures that we're deploying, how close to best practices are there? Are these mature best practice approaches, or are we sort of reinventing the wheel on our own and trying to do some cutting edge things that no one else is really doing, which obviously raises the risk factor? And then how well will these particular components scale? Some of them, the scaling option is not really relevant, but in many of them, it will directly impact our ability to scale as an organization, in particular the Postgres database layer. And so that provides us with another sort of risk factor. And then the technology fit, if we're a Java shop and we do JDBC, and then someone comes and says, well, let's do Ruby because I think it's really cool, and nobody in the organization knows Ruby, then that's going to raise our risk factor. And the combination of those three ratings, if you will, or gradings, allow us to come up with a single risk factor for each area, and that's part of our initial assessment. And then we collect the metrics related to those on a regular basis, and in general, we will get together with the client and do a monthly readout of what did we collect, what does our baseline look like, what have we done in the last month, and how has it changed our risk factors. And that allows us to do a couple of things. One is it allows us to keep track of what's the highest priority, obviously the biggest risk factors, and then allow the client to make minor adjustments, but nonetheless be focused on the biggest risk factors before we tackle the ones that really don't matter in terms of scalability at the end of the day. And then it allows us also, when we start deploying some changes, to come back and show how that risk factor is moving, hopefully in a downward direction across the board, so that the company can ultimately scale their organization with confidence. Just as an example, this is typical of what we generally see when we take this approach. So we'll come in and we'll do our rapid review, for example, and in order to do that, we will deploy some metrics collection, which usually includes pgclue and pgbadger in an automated fashion. We will make sure that we tackle the backup and recovery area. We'll come back with the risk assessments and the monthly reporting, which leads us to changes in all these areas that I just talked about. And then, as an ongoing monthly assessment, we will feed those changes and the reevaluation of those risk values back into the process, which go into the next monthly report. So from month to month, we can start to see what have you guys done for me in the last month versus the last 6 months? Is it valuable for us as a client to keep you around? Are you actually moving my organization in the right direction? So on and so forth. So that's kind of it. Any questions, comments, thoughts? Yes?
When you talked about routing connections to different things, what tool were you using for that?
So there's a number of different ways to do that. The last time we did that was with the JDBC shop, and they were using the JDBC connection pooler. So the application itself was redirecting based on the incoming connection criteria, was connecting to the right backend database. Of course, we could use a web connection pooler or load balancer to do the same thing, and I've seen that done as well. Or we could use something like pgpool or pgbouncer to affect, depending on specifically what you want to track your connections by, there's a number of tools to do so. Anybody else? Well, thanks everybody. I appreciate an opportunity to talk. If anybody has any questions after the fact, feel free to pop me an email. I will get my slides uploaded for the conference, and my email is on one of the first slides there.